Welcome back. Today we are going to start talking about synthesis of industrial polymers. So, the topic of today, which is going to be the continued theme for the rest of the course, that is the synthesis of industrial polymers. I did not mention what kind of polymers and what not, because we will see as we go along. There will be some step polymers that we will talk about, and maybe some of the radical polymers, radical chain polymers that we will talk about. So, a quick recap of what has gone on in the past couple of weeks. Close to maybe 1.5 weeks, we have talked about chemical reactors. In general, for simple chemical reactions, how the principles could be applied in order to design a chemical reactor and in order to choose the reactor that you would like to use. We also talked about selectivity of reaction and as a relationship to that, what kind of reactors you could use. We also talked about comparisons of different kinds of reactors when you have a specific conversion is mined and the reactors are operating at some specific temperatures defined by the operating conditions, which one you will choose for higher conversion, so on and so forth. So, several such problems have been done. And also we talked about what you call as simple mole balance, energy balance, and lots of problems we have done in order to consolidate those concepts, and towards the end we talked about multiplicity of steady states, so on and so forth. And this culminated to a problem on polymerization, where we showed how we can derive the different steady states, exothermic polymerization reaction, and we of course had simplified assumption that your Kp, that is the rate constant of propagation, rate constant of termination, those things do not change with conversion. Initiator concentration does not change with conversion, neither does the initiator efficiency. So, all those things we have discussed, and we have consolidated the concept of chemical reactors. So, now is the time to move forward to the last topic, as I had also mentioned in the concluding stages of the last class. So, what we are going to do is we are going to talk about the structure, mainly the structure property relationship of different kinds of commercial polymers. I mean, in terms of also the synthesis, how we are going to synthesize those, and more like the chemistry aspects of them, and how the differing structures of different polymers, they will have effect on their corresponding properties at the end. Okay. So, we start then. If you remember from our very first class, we had talked about this classification of polymers, and we talked about these commodity polymers and engineering polymers and also specialty polymers. Polymers. And if you remember, we said that these are used for ordinary household applications, and engineering polymers, they are actually used for higher end applications. They can withstand higher temperatures. Specialty polymers, they are more costly to prepare, but they can be used even higher temperature, even better mechanical properties than engineering and commodity polymers. Commodity polymers have the lowest mechanical property. Lowest means the say for example, if you are looking at the quality of the mechanical property that you are looking for, that mechanical property is lower here, means it may be not very robust in terms of the stiffness or in terms of stability as a function of temperature, so on and so forth. So, those things we have discussed, and we told, say for example, here you have low density polyethylene, high density polyethylene, those are some of the examples. Okay, polypropylene or PVC, polyvinyl chloride, like that, or polystyrene. Engineering polymers, it could be polyesters or say polyamides or nylons, polycarbonates, so on and so forth. Polyurethanes, like this, and specialty polymers, say polyimides, it could be polyimides or ether ketone, ultra high molecular weight polyethylene, ultra high molecular weight polyethylene, like this. Okay. So, what we are going to start with is we will start with the preparation of polyesters today, and what I have chosen for this particular class is polyethylene terephthalate, which is your PET. This is polyethylene terephthalate. Okay. Now, this polyethylene terephthalate, as you can understand, this is an ester, and this is an ester of terephthalic acid and ethylene glycol. Then what you get is polyethylene terephthalate, and the structure will be this, like this. At the end you have OH and then CH2. This is the alcohol part. It is very important to be able to write down the structure correctly, and here this is the acid part. It could of course end with an acid, but for reasons we will discuss after. Basically on both sides you will have the alcohol. Remember, in this case the ends cannot react with themselves if you are using one of them in excess. So, this is your PET, polyethylene terephthalate. Now, there are basically two processes which can be used to synthesize this particular polymer. One process is DMT process. DMT stands for dimethyl terephthalate. So, basically your starting material here is the methyl ester of terephthalic acid. Okay. So, this is the methyl ester. You react the terephthalic acid with methanol and you will get the methyl ester. This is the starting material. So, that is why the name is there. That is a dimethyl terephthalate process, and another process is your terephthalic acid process. You start with terephthalic acid. So, that is TA, that is terephthalic. Another process is a TA or terephthalic acid process. So, first we are going to talk about this dimethyl terephthalate process. So, basically this DMT dimethyl terephthalate process, this is a two-stage process. The first stage is what you call a trans-esterification. Trans-esterification. So, here you are doing an ester exchange reaction. So, you start with your dimethyl terephthalate, as I told, this is where the name is derived from. So, you start with your dimethyl terephthalate, you react this with ethylene glycol. Basically, you are using an excess of ethylene glycol, EG, ethylene glycol. So, what will happen is that this ethylene glycol will replace the methanol in this ester. That is why it is a trans-esterification process. The alcohol part of the ester is replaced by another alcohol, so that the methanol is liberated. So, basically what you will get is this particular product OH, CH2, CH2O, CO, okay. This is the product that you will get. So, this is bis hydroxyethyl terephthalate, bis hydroxyethyl terephthalate. Okay. So, this is used in excess, the alcohol is used in excess, and here your methanol is also produced, and this methanol has to be continuously distilled off in order for the reaction to progress towards this side. Importantly, the molar ratio of your DMT to EG, the molar ratio is basically 1 is to 1 point, around 1 is to 1.5. I will talk about the reason why it is 1 is to 1.5 and not 1 is to 2. I mean, you can think about it. Basically, you have only one molecule of this, and if you are putting two molecules of this, then you can have a balanced equation. So, basically 2 molecules of this reacts with 1 molecule of this to replace 2 molecules of methanol, but for reasons I will mention after, you are using 1 to 1.5. This is the first point. Secondly, the melting point of dimethyl terephthalate is around 142 degrees Celsius, but what you do is you do the reaction in a situation where your DMT is molten, it is in molten condition. So, that means you start with a temperature which is higher than 142 degrees Celsius. So, I have the specific values with me. So, basically you start the reaction at 150 degrees Celsius, you start it at 150 degrees Celsius and then you raise the temperature gradually to 200 degree Celsius. Of course, you are doing these reactions under nitrogen atmosphere, so on and so forth, because in presence of oxygen the systems, I mean afterwards the polymer that is produced and all those can have degradation, so on and so forth, and this reaction is done under normal pressure, you are not using high pressure and all. And initially you are using 150 degrees Celsius, which is higher than 142. So, you are working in a molten condition and then you are raising the temperature gradually. Of course, you could ask why we are not going directly to 200 degrees Celsius and why we are increasing the temperature gradually. One reason is that you want to avoid sublimation of dimethyl terephthalate, and that is the reason why you directly do not apply a very high temperature, you start with low temperature and gradually you go to high temperature. Now, one other point that we should mention here, that you have to use a catalyst in order to have a reasonable rate of this trans-esterification reaction. So, you know that why it is trans-esterification, why you are doing a high temperature, because you also want to distill off the methanol and you want this to be in a molten condition. Okay. So, this kind of reasoning is very important. So, you will see throughout the rest of the course this kind of reasoning we will try to provide wherever possible the explanations, and we will try to correlate the structures with the properties that come like that. Now, the catalyst that you are going to use here, because if you do not use catalyst, the reaction does not progress even to a satisfactory yield even at this temperature, then you need very high temperature, which is not practical for this situation, because then these can decompose at those temperatures. So, basically in order to do the reaction at what we call a moderate temperature, we use catalysts, and these catalysts are typically they are acetates of calcium, magnesium, zinc, cadmium, lead and cobalt, and typically they are used at 0.01 to 0.1 weight percent with respect to your dimethyl terephthalate. Okay. And the goal here is to observe quantitative conversion of your DMT into your bis hydroxyethyl terephthalate, or the product here in this case, because if you have a methyl ester group present, that can interfere with the subsequent reaction, because this is not yet your polymer. You see, this is not yet your polymer, you are still not arrived at the polymer. This is the first step of the reaction. Now, the second step of the reaction is polycondensation. So, you have obtained this bis hydroxyethyl terephthalate, and then you do a polycondensation of this product in the same container. So, basically this is what happens, you have your bis hydroxyethyl terephthalate. So, look at the name and the structure, it is easy to remember the name from the structure if you apply the logic. So, CH2 OH, yes. So, n number of these molecules, so they will react and they will produce ultimately your product, which is your PET. And n minus 1 molecules of ethylene glycol will be liberated. Now, how this reaction progresses, basically you can visualize this. This is also kind of ester exchange reaction, So, basically the same alcohol is exchanging with the same alcohol, I mean the same structure of the alcohol is exchanging with another alcohol. So, ultimately what you will see, so maybe one of these molecules can react with another of these molecules through this oxygen. So, what will happen is that, so this will basically attack another molecule over here and liberate say one molecule of ethylene glycol. So, basically then you have extended the chain. So, if you envisage a reaction of one molecule of this with another molecule of this from this alcohol side. So, what will happen is that this alcohol will attack the ester linkage of another molecule and liberate this alcohol. So, basically instead of now one aromatic unit you have a chain which has two aromatic units, so on and so forth. So, ultimately it can go on and on like that, and it can have what you call as polycondensation, condensation because ethylene glycol is removed at each step. So, this is why we call this polycondensation. So, you see that there are two steps involved here, transesterification and polycondensation reaction. Now, what you do is that after the transesterification reaction is complete, whatever excess of ethylene glycol was there, that you have to remove. The ethylene glycol boiling point is around 197 degrees Celsius. So, what you do is that you gradually increase the temperature from 200 to 250 degrees Celsius. Once the transesterification reaction is complete, the first step is complete, you gradually increase the temperature to 250 degrees Celsius, and then you distill off all of this ethylene glycol, residual whatever ethylene glycol was there unreacted, that you distill off, and afterwards what you do is that you further increase the temperature to around 270 to 280 degrees Celsius, and you apply a reduced pressure, that means you apply vacuum to the system. So, it is basically 60 to 130 Pascal, that is the pressure that you have here. So, 1 Pascal is close to 10 to the power actually 1 atmosphere is close to 10 to the power 6 Pascal. So, you have some idea. So, this is atmospheric pressure is around 10 to the power 6 Pascal. So, you have some idea how much you have to reduce the pressure, and under this condition also you are creating this ethylene glycol to the system, that also you have to continuously distill off, and you can use of course a catalyst to accelerate this reaction. In principle, the same catalyst that you have used for transesterification reaction in the first step could be used here also, but the problem here you have already gone to very high temperature, and at these temperatures the presence of those catalysts, your calcium acetate or magnesium acetate or zinc acetate, those can actually decompose your product. So, the thermal stability of your product can be compromised in presence of the transesterification catalysts that you have used in the first step. So, what you do is you use what you call as a dual catalyst system. That means, for the second step, when you are going to the second step, what you do is the catalyst that was used in the first stage, that is still in the reaction mixture, that is deactivated. So, you deactivate by addition of an alkyl phosphate. So, you have deactivated your catalyst for the first reaction. Now, for the second reaction, what you do is you add antimony oxide, which will act as the catalyst for the polycondensation reaction. So, this is the overall process of polycondensation. So, you see some of the details are important here, and you will stop the reaction when the desired melt viscosity is reached, because depending on the viscosity of the product you can use for a specific application and all. Now, this polycondensation reaction that you are talking about, in order for this reaction to be rapid, whatever ethylene glycol that is produced has to be quickly removed, and this is something that you can achieve by using a good stirrer to have an intensive mixing, because when you have intensive mixing, that increases the polymer melt surface area also, and so that gives you more chance for this liberated ethylene glycol to diffuse out and go into diffuse out and get distilled out. So, that is why what you do, your stirring is very important, so that you increase the polymer melt surface area, because the temperature is 270 to 80 degrees Celsius that you are using, your polymer will be in a molten situation, molten state. So, whatever ethylene glycol has come out, if you have the melt surface higher, the distillation will be easier for the ethylene glycol. Now, how do you know you have reached the desired melt viscosity? The power consumption of the stirrer motor, the power consumption of the stirrer motor, that will give you an adequate indication of the melt viscosity, because it will consume more and more power if the melt viscosity is increasing, if the viscosity of the reaction mixture is increasing. So, there is a relation between the two, and so from this power consumption data you can actually find out the melt viscosity, and when you have reached the desired melt viscosity you can stop it. So, what you do is that you have a vacuum. So, you release the vacuum by replacing it with nitrogen. So, you put some nitrogen inside the system, and then under the pressure of this nitrogen you expel the melt out of the system, and afterwards what you do is that the melt you can quench with water, and you can make pellets out of the polymer. Now, something that you have to keep in mind here, in this particular process the degree of polymerization or the Xn bar, the degree of polymerization that you can reach is only about 100. Now, in order to obtain a higher degree of polymerization, what you have to do is that these pellets you have to subject them to solid phase polycondensation. You have to subject them to solid phase polycondensation. What you do is that in the solid phase itself you further do the polycondensation, you go to temperatures up to, you heat it up to temperatures of 250 degrees Celsius for around 2 hours, okay, and under vacuum, of course, because remember that when the polycondensation is progressing, your ethylene glycol is being liberated, that has to be removed from the system. So, you go to high temperature, keep for certain time, this has been standardized, and the rate determining step, for this solid phase polycondensation is basically the diffusion of liberated ethylene glycol, which is a byproduct, of course, liberated ethylene glycol from the polymer particles, because they have to come out. So, it is a solid phase reaction. So, they have to diffuse out of the polymer particles, and this rate is the slowest of all the rates that are involved in this reaction. So, this is the rate determining step, and the rate of diffusion, of course, then will depend on the size of the particles of the polymer. All right. So, this is in a nutshell the reaction that is used to prepare polyethylene terephthalate. Now, let us come back to this particular reaction again, the transesterification. I told that we are using 1 to 1.5 and not 1 to 2. In actuality, you would expect I would use 1 to 2. Now, keep in mind, if you are using 1 to 2, you are going to get only this product. As the stoichiometry demands 2 molecules per 1 molecule of this, you are going to get only this product. However, if you are using less than that stoichiometric requires, say 1 to 1.5, you will get something else also along with this product. You are going to get some oligomers which have very same structure as the polymer. So, what you will get other than your bis hydroxyethyl terephthalate, also what you will get is that you will get some linear oligoesters of the general formula like this. So, basically I mean you will still have some of these to react with, because if you just reacted 2 molecules with this, then this will be the product that is produced, but if you have taken this less, then what will happen is that the proportion of this part, the acid part, might increase in the product. So, along with this particular product you will also get some of these particular product, which is a linear oligoester. Of course, this has the same formula as your product, which is your polyethylene terephthalate, but basically this is not a polymer, this is linear oligomers, this n value is small. So, you will have some degree of polymerization to start with in the transesterification step itself. So, that is the reason why you are not using 1 to 2, you are using say 1 to 1.5. Now, so these linear oligoesters will be produced, and the average degree of polymerization, of this linear oligoester that is produced in the first step, that is transesterification step, that will be depending on the ratio of ethylene glycol to dimethyl terephthalate that you are using. If you are using 2 to 1, which we are not using in this case, you will get only bis hydroxy ethyl terephthalate. You will only get bis hydroxy, bis means there are 2 units of this, that is why it is bis, and this is hydroxy ethyl. So, bis hydroxy ethyl, and this is a terephthalate ester linkage. So, that is bis hydroxy ethyl terephthalate. So, you will get only bis hydroxy ethyl terephthalate. Now, if the number of moles of ethylene glycol is lower than 2 times the moles of DMT, that means say 1 to 1.5 if you are using say, then you will get a higher value of N, So, instead of 1 to 2, if you are using 1 to 1.8, then you will get some N value. If you are using instead of 1 to 1.8, you are using 1 to 1.5, then you will get higher N value, so on and so forth. So, you will get something like what you call as a pre-polymer that you can subject to further polycondensation step in the next process. The same reaction mixture, you are increasing the temperature and slowly you are distilling away all the unreacted ethylene glycol that was present, because the boiling point is 197 degrees Celsius, and after that you are also destroying the catalyst that you had used in the first step, because that will compromise the thermal stability of the product, and you are adding another catalyst. That is why it is a dual catalyst system that you are using. Okay. So, these are some of the main important parts that I wanted to talk about. Now, we can of course, so this is your dimethyl terephthalic acid route. Another route that we can talk about is terephthalic acid route. I told you that there are 2 routes, one is the DMT route, dimethyl terephthalate, another is terephthalic acid route. Now, this route was initially not used because economic processes to produce pure terephthalic acid were not available initially, that is why people were using DMT. Now, DMT is not a direct process, because you know you are using a transesterification in the first step. So, this terephthalic acid route is something that is that people are using much more now that we have all these economic processes to prepare the terephthalic acid. So, something that you have to keep in mind is that in this particular reaction that you do, you are using a direct esterification route. So, which is nothing but reacting with your terephthalic acid. So, this is your terephthalic acid, you react with your ethylene glycol and you get your BHET, which is your bis hydroxy ethyl terephthalate. I mean, instead of transesterification, you are using a direct esterification route to obtain your bis hydroxy ethyl terephthalate. Now, why we will use this terephthalic acid route and not dimethyl terephthalate route, we will tell you after the advantages of this route afterwards. So, you directly get your BHET, and in this process, so 2 molecules of this can react and 2 molecules of water can be evolved. Okay. Water you have to remove by distilling out. Now, this particular process that you are using here, one difference here is that this terephthalic acid, you are not using any other solvent, right, you are using this plus this. So, terephthalic acid has a sparing solubility, it is not soluble to a large extent in ethylene ethylene glycol. So, this direct esterification route if you are going to do, you have to use a high pressure, around 3 to 5 bar of pressure you have to use. Just to compare it with your normal atmospheric pressure, 1 bar is approximately equal to 1 atmosphere. So, 3 to 5 bar of pressure you have to use, and you are basically using a high temperature in the range of 220 to 260 degrees Celsius in order to do this direct esterification step. Compare this with your trans esterification step that you used for the synthesis of BHET in the first step of the DMT process from the dimethyl terephthalate. This process, this reaction temperature was much lower. You start with 150 degrees Celsius, you go to 200 degrees Celsius. The reaction temperature now is much higher, 220 to 260 degrees Celsius. The pressure that you used here was normal atmospheric pressure, here you are using 3 to 5 atmospheric pressure, simply because you are using instead of dimethyl terephthalate, you are using terephthalic acid. This reactant remains the same. So, the solubility is also important. Now, in this case here this melts and it forms a homogeneous mixture. Now, in this case this particular material terephthalic acid, it has sparing solubility, it is sparingly soluble. So, you need to go to high pressure, go to high temperature in order to effect this reaction. So, what we will do is that we will stop here today and we will continue the discussion of the terephthalic acid route in the next class, because this is not the end of the terephthalic acid route, this is just the first step. So, we will continue hereafter the discussion of this, and so the topic remains the same. We keep talking about the synthesis of different step growth polymers, and our time is up for the day. So, we will see you in the next class. Until then, thank you and goodbye.